We usually view a melting scoop of ice cream as a ruined dessert. In reality, it's a demonstration of nature's default state, heat. Before frozen treats could exist, humans had to overcome the absolute scarcity of cold. For most of history, ice was a strictly geographical and seasonal resource that vanished the moment it was needed most. The first major breakthrough in capturing that resource happened over 2 millennia ago. This mud brick yakhchal represents the innovation stack's base layer, passive cooling architecture. Long before mechanical cooling, Persian engineers used these structures to trap winter ice in the middle of the desert. Thick wall insulation and deep underground storage vaults allowed them to lock out the sun for months. Engineering triumphs like the yakhchal established the first layer of the ice cream platform. Mastering the capture and storage of cold as a reliable resource was the prerequisite for every culinary invention that followed. Once cold was capturable, the process needed a standardized set of instructions. The technology of ice cream required a reproducible protocol to move beyond palace walls. That protocol arrived in 18th century cookbooks and reached the American colonies by the 1780s. At Mount Vernon, George Washington purchased a cream machine for ice in 1784, documenting the equipment needed to turn cream into luxury. Despite having the cream machine, production remained a grueling manual task. During the summer of 1790, Washington's records show roughly $200 in ice cream-related spending, a massive investment in hospitality and social signaling. Even with a codified recipe, ice cream remained a status symbol for the elite. To reach a wider audience, it needed a way to move across the globe. Frederick Tudor solved the distribution problem by building a logistics network for cold. He harvested massive blocks of frozen New England lakes, insulated them with sawdust, and monetized the entire supply chain. This animated map shows the scale of Tudor's network. In 1833, 180 tons of ice left Boston for Calcutta. After a 4-month voyage, nearly 100 tons arrived intact on the other side of the world. This consistent global supply route created a permanent demand for chilled goods and frozen desserts in tropical markets that had never seen ice before. But the natural ice industry fell into a classic incumbent trap. They had optimized the harvesting systems so well that they couldn't pivot when mechanical refrigeration emerged to manufacture cold on demand. Artificial ice plants and industrial factories, like Jacob Fussel's 1851 operation in Baltimore, applied manufacturing logic to the product. They shifted the mastery of cold from nature to the factory floor. Mechanical replication democratized the dessert. Scaling the technology turned an artisanal luxury into a mass-market commodity available to anyone with a few cents. As the market grew, it hit a final bottleneck: the user interface. Vendors lacked a sanitary, efficient way to serve thousands of people on the move. This glass vessel is a penny lick. Customers bought a scoop, licked the glass, and handed it back to the vendor for a rinse. It was a sanitation nightmare requiring constant washing and forced customers to stay near the cart. Crowded environments like the 1904 St. Louis World's Fair drove a wave of parallel experimentation. In this high-density market, vendors looked for a way to serve ice cream that was portable and disposable. The edible cone provided the perfect solution. It functioned as both packaging and product, eliminating the need for washing and allowing customers to carry their dessert through the fairgrounds. Edible packaging was the final link in the chain. It fully opened the ice cream platform to the mobile, modern consumer. In the modern era, innovation has moved past physical infrastructure and into molecular engineering and biology. We are now optimizing the dessert at the level of the individual protein. This financial trajectory reflects the scale of the modern platform. Global value is projected to reach nearly $170 billion by 2033, fueled by a rise in artisanal, plant-based, and healthier alternatives. To meet this rising global demand, scientists are actively using the process of precision fermentation. They are engineering specialized microbes to produce dairy proteins without cows, creating a final product that is molecularly identical to traditional ice cream. At the University of Wisconsin, researchers introduced plant-based polyphenols to create a fat-protein network that physically resists flow. This allows the scoop to hold its shape at room temperature for over 4 hours. The ice melts, but the protein stands. Rewriting the product's biology allows it to bypass its oldest environmental constraints. By manipulating these networks, we can maintain a frozen experience even as surrounding temperatures rise. This story spans thousands of years, from ancient desert icehouses to global shipping networks, from disposable glassware to precision-engineered microbes. What looks like a simple dessert is actually a composite of these stacked innovations. It represents the successful transition of cold from a rare, seasonal luxury into a permanent, global, engineered utility.